Hello and welcome to our second chapter, which deals with electric current, which is the motion of electric particles or charged particles, and is going to eventually give rise to the magnetic field and magnetic forces. But it is also important in its own right, just because this is how information is conveyed and how electricity moves through wires. So when you're looking at your lights or your computer or your phone or anything like that, that is going to be because of an electric current that is occurring. For current to flow, there must be a difference in potential energy analogous to the flow of heat between different temperatures or of water between different altitudes. Just as water current is the flow of H2O molecules, electric current is simply the flow of electric charge and is measured in amperes. 1 ampere is a rate of flow equal to 1 coulomb of charge per second. So on the right-hand side, you see a kind of analogous system to electric current where water will flow from a higher pressure to a lower pressure or from higher potential energy to lower potential energy. In the same way, a current will flow from a higher electric potential to a lower electric potential, such as might happen if you disconnect a battery from a capacitor and let the charges flow back to their initial states. However, this would be really quick and it wouldn't get much accomplished. So what you need to do is you need to do something that is analogous to placing a pump in an electric or in a water system and place a battery or some potential difference that is going to push the electric current through repeatedly instead of just pushing it through once until all the charges are redistributed to their original states. So another thing that I want to note is that electric current is usually the flow of electrons, which are negatively charged, but an electric current is measured as a positive charge. So if a current is pointing to the right, then the actual flow of electrons will be flowing to the left because they have opposite charge from what the electric current is telling you. Batteries and electric generators do work to pull negative charges away from positive ones. In chemical batteries, this work is usually, but not always, done by the chemical disintegration of zinc or lead in acid, and the energy stored in the chemical bonds is converted to electric potential energy. Generators, such as alternators in automobiles, separate charge by electromagnetic induction, a process which we will describe in a later chapter. The work is done by whatever means in separating the opposite charges is available at the terminals of the battery or generator. These different voltages of energy per charge create a difference in potential voltage. This voltage provides the electrical pressure to move electrons through a circuit. One of the more fundamental rules for electric current is Ohm's law, which states that current is equal to the voltage or the potential difference in energy divided by the resistance, where resistance just does what it sounds like and tells you how resistive the object is to a flow of current. So if you try to place a current across a stone, then that's going to have a large resistance because the current doesn't want to flow through the stone. It's just going to flow very slowly. Whereas if you place a voltage across a metal, that's going to have very low resistance, bordering on zero resistance, which corresponds to a high conductivity. Amperes are given by the units of volts per ohm, and the resistance of a typical lamp cord is much less than 1 ohm, while a typical incandescent bulb has a resistance greater than 100 ohms. An iron or an electrical toaster has a resistance of about 15 to 20 ohms. The damaging effects of electric shock are the result of current passing through the body. What causes shock in the body, current or voltage? From Ohm's law, we can see that the current depends both on the voltage that is applied and the electrical resistance of the human body. The resistance of one body, which depends on its conduction, ranges from about 100 ohms if it is soaked with salt water to about 500,000 ohms if the skin is very dry. If we touch two electrodes of a battery with dry fingers, completing the circuit from one hand to the other, we can expect to offer a resistance of about 100,000 ohms. We usually cannot feel the current produced by 12 volts, and 24 volts just barely tingles. If our skin is moist, 24 volts can be quite uncomfortable. The current through the body has different effects depending on the current that passes through. For about 0.001 amperes or 1 milliampere, the effect can be felt, but about 70 milliamperes will cause serious disruption, probably fatal if the current lasts longer than 1 second. This is dependent on the resistance of the body, where if we have the resistance of a dry body, we and accidentally touch both ends of a plug or something so that our fingers are touching 120 volts apart from each other, then you're going to feel a little bit of pain. It's going to be about 0.05 amperes. But if you're wet and you don't have that 100,000 ohm resistance, instead, it can be fatal for the same voltage to be applied across you, which is why you don't want to use a toaster in a rain shower. There are two types of voltages. DC voltage, which stands for direct current and provides a constant current versus time, and AC voltage, which applies an alternating current or a sinusoidal current versus time. The DC and AC are both useful for different things. DC was is used for many of our household appliances, and most of the things in our house are going to use DC current, including our laptops. And AC current is much more useful for transmitting current over long distances without losing a lot of power. So what we end up having is an AC current which goes from the power station through the power lines and to your house and comes out of your house at 120 volts, and DC current, which is what actually powers our appliances. So how does this happen? How do you convert between DC and AC, or AC and DC as the case may be? So what happens is you have an AC-DC converter where you take an alternating current and pass it through something called a diode, which is a semiconducting device that only allows positive current through. If this is the case, then you go from A to B in our diagram, where you cut out all of the negative parts and just have a bunch of humps that look kind of like an AC current, but not exactly. Then you use a capacitor, which, in addition to being used to store energy, is also something that can store charge. So as you pass a voltage or the positive voltage over a capacitor, then it is going to store a charge. And as you have the zero voltage or the decreasing voltage rather across the capacitor, then it is going to start dissipating charge, but it is going to dissipate the charge slower than if you just had a voltage across a wire. So with the capacitor, you are able to see this little kind of wave, kind of DC current that you see in C. And then practically, you actually use two diodes so that the AC current, rather than just turning off half the time, will be positive all the time, going up and down and up and down in little humps instead of going up and down as a sinusoidal wave. And using the capacitor, you are able to approximate a straight line versus time, which is what a DC current is. And we are able to use that to power our devices and to power our appliances. Current is established through the wires at nearly the speed of light. It is not the electrons that move at the speed. Although electrons inside metal at room temperature have an average speed of a few million kilometers per hour, they make no current because they are all moving in all possible directions. This net flow of electrons that is caused by applying a voltage is called the drift velocity. In a typical DC circuit, the electrical system of an automobile, for example, electrons have a drift velocity that averages about 100th of a centimeter per second. This is not the speed of light, or even nearly the speed of light. What happens instead is that the electrons will cause there to be a propagation. There will be an electric field which pushes one electron forward and pushes the other electrons forward as you apply this potential difference. When you plug a lamp into an outlet, energy flows from the outlet into the lamp, not electrons. Energy is carried by the pulsating electric field and causes vibratory motion of the electrons that already exist in the lamp filament. When you apply a battery to a wire, you are applying a potential difference, which is going to cause there to be an electric field because force moves from a higher potential to a lower potential. This electric field is going to push the electrons forward, but because of interruptions, because of running into other electrons, they only go forward at the drift velocity. What is actually happening to cause there to be a current is the propagation of the electric field and the motion of the electrons causing there to be motion of other electrons, which pushes a current through. The power going through an electric circuit is equal to the current times the voltage, which makes sense unit-wise because it is the energy divided by time. So the current, which is charge divided by time, times the voltage, is going to have units of energy divided by time. A 100-watt bulb, for example, glows brighter than a 60-watt bulb, but most of that power is dissipated by these bulbs is not light, it is heat. At least 90% of the energy transferred by an incandescent bulb is heat. Fluorescent lamps, on the other hand, emit much less heat, which is why you can touch them without burning yourself. Incandescent bulbs are being replaced with CFLs, which are a type of fluorescent lamp that fits into a standard light bulb socket. For the same wattage, CFLs emit much more light and much less heat than incandescents. That's why you can replace a 100-watt bulb or a bulb which takes 100 watts of power to power incandescent with a CFL of about 25 watts and gets about the same amount of light. I now want to define what a circuit is. So a circuit means that something goes around in a track, which is necessary in order for there to be a flow of electrons, because if there was no track, then all of the electrons that go out of one end of the wire would just be lost, and there would be no electrons coming in the other side of the wire to form a circuit or to form a completed track in order for the electrons to go around in circles and circles and continue to flow. So what we see here is a series circuit where the components are placed in order along a wire in order to have the current flow through each of the components, and in this case, they would turn on a light bulb. So you cannot have current flowing without flipping the switch and allowing the current to flow through the switch and completing the circuit. For series circuits, electric current has only a single pathway through the circuit. This means that the current passing through the resistance of each electrical device along the pathway is the same. This current is resisted by the resistance of the first device, the resistance of the second, and that of the third also. So the total resistance to the current in the circuit is the sum of the individual resistances along the path. The current in the circuit is numerically equal to the voltage supplied by the source divided by the total resistance of the circuit. This is in accordance with Ohm's law. The supply voltage is equal to the sum of the individual voltage drops across each device. This is consistent with the total energy supplied to the circuit being equal to the sum of energies supplied to each device. The voltage drop across each device is proportional to its resistance. Ohm's law applies separately to each device. This follows from the fact that more energy is dissipated when a current passes through a large resistance than when the same current passes through a small resistance. Alternatively, we have parallel circuits where instead of the current being passed through all of the components in a row, you have it set up so that the current is free to pass through whatever path it wants to go through. So in this case, you have two switches which are on and one switch which is off, and the current is free to pass through the two switches that are on without worrying about the switch being off. This is a valuable tool and is why Christmas lights used to be in series. And if a Christmas light went out when something was in series, then if a bulb went out, then the entire system would go away. But if a bulb went out in a parallel circuit, then that would just mean that there was more current flowing through the other bulbs. Each device connects the same 2 points A and B of the circuit. The voltage is therefore the same across each device. The current divides among the parallel branches. Ohm's law applies separately to each branch. The total current in the circuit equals the sum of the currents in its parallel branches. The sum equals the current of the battery or other voltage source. As the number of parallel branches is increased, the overall resistance of the circuit is decreased. The overall resistance is lowered with each added path between any 2 points of the circuit. This means that the overall resistance of the circuit is less than the resistance of any one of the branches. Series circuits have the same current running through each element, but the voltage across each is different. The sums of voltages add to the total voltage. Parallel circuits have the same voltage across each element, but the current running through each is different. The sums of the current add up to the total current. So what happens is that because you don't want your power to go out if one light bulb in your house goes out or if a fridge is running improperly or anything like that, you'll generally have every appliance in your house set up to a parallel circuit. But this also means that for every appliance that you add, you are going to have less resistance of the total resistance. What this means in turn is that there is going to be more current for each appliance that you have because it has different pathways to go through. This can be dangerous as we can have fires coming out of this. We can have your house catching on fire if you apply too much current. In order to avoid this, we invented something called fuses, which are elements which are placed in series before the object, before the current starts passing through all of these objects, where if the total current exerts or is greater than a certain amount, the fuse will burn out and the fuse will switch off the power because you're using too much current and it becomes a fire hazard.